part of a course on subRiemannian geometry, we are revising some theory of Lie groups. In the previous video, I recalled the notion of Lie group, Lie algebra, left translation, right translation, left invariant vector fields, and we reviewed how a Lie group homomorphism between Lie groups induces a Lie algebra homomorphism between the Lie algebras of the Lie group. In this video, we will revise first the exponential map between the Lie algebra and the Lie group, and many of its properties. Then we will discuss the general linear group, its Lie algebra, and its exponential map. Let's see. Let's start by reviewing the exponential map on Lie groups. So G will be a Lie group. Small g will be its Lie algebra. So the Lie algebra of G. The map exp from the Lie algebra to the group G is defined as an element x in the Lie algebra goes to what we call exp of x, which is defined in the following way, where, so if we see x as a left invariant vector field on G, then the exponential of x is defined as the flow at time 1 for the vector field x starting at the identity of the group. So this is the flow at time 1. This is the flow of x starting at the point 1, the identity of G. Okay, of course, in this definition, we are claiming that this flow exists up to time 1, okay? So one needs to check that the flow exists, okay? And let me revise a proposition that as a consequence tells you that the exponential map is well defined. So here's the proposition, and it's the following. So let's fix a left invariant vector field on a Lie group G and a curve theta defined on the real line valued into G such that at time 0 is the identity element and its derivative at time 0 is the vector field x evaluated at the identity. These are the identity of the group. Then this curve is a flow line of x. So in other words, it is a solution of the ODE given by x. So the derivative of this curve is equal to the vector field x if and only if it is a one parameter subgroup. We will write OPS, one parameter subgroup. What does it mean? This means that it is smooth, gamma 0, okay, I'll put this in parentheses, this is trivial in this case, gamma 0 is 1, and it's a morphism. So S plus T. So in R here we see that the product is the sum. The operation is the sum. Theta S times theta T. And this is the product on the group. And this is for all S and T in R. Once one observes this fact, then as a consequence, then we have that for all x, there exists one and only one parameter subgroup gamma or theta with theta dot 0 equal the vector field x. So this one parameter exists for all R, one parameter subgroup, and is actually the flow line. So one can consider the flow line at 1. Okay, now why is this proposition true? And is this the key observation in proving that proposition is the following. So if we have a curve gamma defined on an interval AB into G, and is a flow line for x, which between 2 points, let's say from gamma A to gamma B, then we can translate. So suppose we have a curve that goes from 2 points, gamma A and gamma B. Now what we could do, we can translate the curve. So then the curve, so I left translate in such a way that this point goes to this. So I should multiply by, on the left, so I'm using left invariant vector field. On the left, first by gamma A minus 1 and then gamma B. So now compose gamma. So now this is a curve that starts from gamma B. And since I multiply on the left, what I have, this is a flow line of x. Now from gamma B to whatever point it is. Okay, it's not really important, but it's another point. So it's gamma B times gamma A minus 1 times gamma B. And what's important is that this is because the vector field is left invariant. So in other words, if I can consider a piece of a flow line, and we know that for small time flow lines always exist, then what I can do, I can just left translate and have another piece of a flow line. So altogether, I enlarge the domain of the flow line. This tells us the flow lines exist for all times. Okay, so the exponential map is well defined, and here are some properties of the exponential map. I will not prove these properties. They're very easy once you know they're true. You can find them in the lecture notes. So say we have a Lie group, and we fix a left invariant vector field G. So this is the Lie algebra G. Okay, first property. Okay, the exponential, as you say, of x, by definition, this is the flow line at time 1, starting from the identity of the group. Now I will delete here, and I will put time t, and put a t in here. So now this will be true for all t in R. Okay. In other words, really, like if you, this is because changing the speed of the flow line really changed the time when you're following the flow line. But this is interesting to read, because now this means that as a function of t, this curve is a flow line. This is what is written here. Okay, and from what we said before, this means that t going to exp tx, this is a one parameter subgroup. Okay, good. In particular, from all of this, let's remember that we also have that the exponential of 0, this is the identity of the group, okay? This is one more property. Okay, let me write down the fact that this is a groupomorphism. So the exponential of s plus t times x, this is equal to exp of sx times exp of tx. This is for all s and t in R. Another property of the one parameter subgroup, or the fact is a homomorphism, is the exponential of minus x is equal to exponential of x inverse. Okay, these are easy consequences. Let's continue. So one can prove that the map exp, it is actually a map from the Lie algebra to G that is smooth. And this is just because of smoothness on initial data for ODEs. Okay. An easy calculation, but very important, is the differential of the exponential map at 0, right? Which is a map that goes from the tangent of G at 0, since this is a vector space, is the G, to the identity to the tangent at the identity of G, which is the Lie algebra in our one of the identifications. Okay, so this map goes from the Lie algebra to itself, and one can check that this differential is actually the identity map on G. It's a very important calculation, very easy. Do it if you didn't do it at some point. Okay, so as a consequence from the inverse mapping theorem, exponential map is always a diffeo when restricted to some small enough neighborhood of 0 and a neighborhood of 1. Okay, very good. Right, another consequence. If we consider the flow line of x, g, remember this is okay. But now we start from another vector, another point g. Okay, but since x is a left invariant vector field, what we could do, we can just left translate the flow line starting from the identity. Okay. Now, if you see this map as a map in G, this is equal to the right translation by exp tx of G. So it is interesting because here the vector field x is seen as left invariant vector field on G. So what we have is that flows of left invariant vector fields are right translations. Okay. Similarly, let's write it. Similarly, if we take the flow of a right invariant vector field that coincides at the identity with x, then we get that this is the left translation by exp tx of G. So when here this is a right invariant vector field. Another thing to observe is that if we flow, these two formulas tells us that if you flow along a right invariant extension of a vector at the identity for any time t, starting from the identity, you go to the same point if you consider instead left invariant vector field associated to x and you flow from the identity. Okay, so the right invariant extension of a vector and the left invariant extension of a vector, these are different unless the group is commutative. Okay, so these are two vector fields, but it's interesting that they have the same flow lines when they start from the identity of the group. Okay. Now, one more property, and this is very important to us. So recall that we saw in the previous video that if you have a Lie group homomorphism, then you can associate at the level of the Lie algebras. So G is the Lie algebra of capital G, H is the algebra of capital H. You can associate a Lie algebra associated or induced associated. Now, what is true is that, okay, we have on G to H, we have the map F. At the level of the Lie algebra, we have the map F star. If we consider now the exponential maps on the two groups, then this diagram commutes. So, in other words, we have the formula that exponential composed with F star is equal to F composed exp. Okay, this is a formula that is very useful and will be used to deduce quite a bit of identities on groups. Okay, so and all right. A remark about the exponential for those that have seen some Riemannian geometry, because also in Riemannian geometry there is an exponential map. Okay, so if we see the algebra as the tangent identity, this map is not the Riemannian exponential. This is, let me say, is very rarely the exponential map with respect to a Riemannian or some Riemannian structure. Okay. Okay, so there is no, for only for very particular groups and particular distances, metrics, Riemannian metrics on groups, then the exponential map is the map induced by Riemannian geodesics. Now we will revise a very special group, the general linear group, for two reasons. One reason is that some of the maps that one considers on Lie groups are actually valued in some general linear group. And second, because since eventually our interest will be in nilpotent groups, then it's actually true that all the nilpotent groups can be seen as a subset of a general linear group. Okay, so we're going to revise a general linear group, and its Lie algebra and its exponential map. Okay, so one starts with V, finite dimensional vector space, and of course one can think of V to be Rn for some n natural, but it is also very good to think of V as the Lie algebra of a Lie group. This seen as a vector space. Okay, and after that one consider the group of linear invertible linear transformations on V. So all the maps from V to V that are linear and bijections In other words, these are isomorphisms of vector spaces. So also when we will consider G, then this will be just maps that preserve the linear structures. Okay, and just as a notation, GLNR, this is the general linear transformation for the group, for the vector space Rn. Now, this is a group because, so the product on GLV is the composition of maps and okay, since they are invertible, it's easy to prove that this set with this product is a Lie group. Okay, so maybe it is clear that okay, this becomes a group. So this becomes a group. Now let's clarify the fact that it's also a manifold. So think of V to be just Rn, right? So as vector space. Now GLV. So or maybe if V we identify their linear isomorphism as Rn, we can see GLV as GLN. What are these? These are the invertible linear transformation that we can interpret with as n by n. So this is the space of n times n matrices, and these are exactly the matrices that are invertible. So in other words, with that non-zero determinant. And in the n times n matrices, this is a vector space of dimension n squared, n times n. Moreover, this inclusion here, it's an inclusion for which this object becomes an open set, right? It's determinant different than zero. So it's an open set. So this is this includes as open. As open subset. Okay. In other words, so GLV up to this identification is an open subset of Rn squared on which operations are smooth. Actually, they are even analytic. And therefore, by definition, GLV is a Lie group. Very good. Okay. Now let's move to the Lie algebra. For now, let me first introduce a notation. So V, a vector space. We define GL. So now these are GL in Gothic fonts. GLV. So this is an L. GLV to be the space of all the linear transformations linear of V equipped with the bracket AB, bracket between A and B is AB minus BA. We discussed briefly in the previous video this definition, okay? And GLV equipped with this bracket is a Lie algebra. Okay, now the important fact is that the Lie algebra of the group GLV is canonically isomorphic to GLV. That's why we chose these names. Okay. Now, let me briefly say what is this isomorphism and why this is true. Okay, you can fill the gaps. So indeed, so the Lie algebra of GLV. Okay, this, let's see it for a moment just as the tangent at the identity. So this is true as a set. Now, the tangent at the identity of this group, since this group is an open set of all the transformations, the two spaces have the same tangent. So here I'm using the fact that GL is an open subset of small gl. And just because these are those with determinant different than 0. Okay, and because this is a vector space, then the tangent at a point is isomorphic to the vector space itself. So GL is a vector space. Okay, so at least set-wise, we have an identification between this vector space and this vector space, okay? And now I'm claiming that, moreover, this identification preserves the bracket operation, and namely, so here a bracket in here is equal to the bracket in here under this identification. And moreover, so let me clarify how an element in a small GLV induces really a left invariant vector field. And for all A in GLV, the map that for each B in G associate AB, this is an element GLV, this maps defines a left invariant vector field on G. Okay, so check that this rule gives a left invariant vector field on G. And after that, just check that bracketing the two vector fields of this form is the same of bracketing elements A and A prime in this Lie algebra. Okay, now let's discuss the exponential map. So first of all, let me quickly recall you the matrix exponential. At some point in your studies, you have probably saw the theory of taking exponentials of matrices. Now I will do it just but abstractly, not giving, not not really writing the dimension n of the vector space. Suppose you have a V, a vector space, and if I fix an element A in GLV, which again, if you do it identify, I'm just saying fix an n by n matrix. Then you define e to the A to be the map that is the identity plus the map A plus 1/2 A times A square, 1/3 factorial A cube, dot, give you the rule. This is the sum over k from 0 to infinity of 1/k factorial of A to the k. Okay, see that this operation do not depend on how you identify your vector space with Rn. And let me clarify that this capital I, this is the identity map, which is an element in V, sorry, it's an element in GLV. Okay, I'll make you notice that the series converge, actually it's absolutely convergent. And the very important fact is that the map that to every element A in GLV associate e to the A valued in GLV. So it's quite easy to show that this object is invertible. Actually, the inverse is e to the minus A. Maybe I'll write this at some point. E to the minus A is equal to EA minus 1. Then this map is actually the exponential map for the Lie group. GLV. So this is a Lie group, this is its Lie algebra, and this map is the exponential map. Actually, that's why the exponential map for arbitrary Lie group is called exponential map, because it's an extension of this theory, the generalization of this theory. Let me write down some formulas that are important for the matrix exponential, but we will see that have actually generalizations. So if two matrices commute, let me write it like this, then the exponentials commute, and actually their value is equal to e to the a plus b. Second property is that, okay, and from this you also see that if I put b equal to minus a, then I get the inverse. So e to the b minus 1, this is equal to b e to the a b minus 1. 3. The determinant of e to the a, it's equal to e to the trace of a. And if you take the derivative of the curve e to the ta as a function of t, then you have a to the e to the ta. And in particular, if you evaluate at 0, then you have a. So first of all, these formulas, these are just saying that okay, you can prove them directly. They're very easy. But again, we know that, so from what I've stated, that this is the exponential of the Lie group. So this means that this is not only a one-parameter subgroup, this is also a flow line of a vector field. Which vector field? Exactly A, right? And if I want to, so this is the derivative of the identity, so it's A. And then for any other, at any other point, I just have the translation of A. Regarding these formulas, we will see that something more general is true. So we don't really need to prove, or maybe you have to prove it when we don't know the theory of Lie groups. But once you know it, you will see that these proofs are particular cases of more general formulas. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.